How would the universe change if you approach the speed of light? What would everything around you look like? How would space and time act? The answer is a lot different from what you are currently used to. To travel the speed of light isn't actually possible for anything other than massless particles, like photons. It would require infinite energy to get something with mass to that speed. The energy required exponentially goes up the closer you get. But there are instances of matter coming close. We've observed some particles traveling 99% of the speed of light. Now for you and me, we have no hope of ever approaching these speeds. But if you did manage it, what happens to space and time from your perspective would be very noticeable. Let's ease you into this, as it's going to be a bit tricky to wrap your head around. We will simulate going from standing to traveling almost the speed of light. This is a fun little game called A Slower Speed of Light, released by MIT, demonstrating what would happen if the speed of light got progressively slower, eventually to walking speed. At first, my character looks around and sees the world normally, but as I start to pick up these orbs, instead of speeding me up, the game slows the speed of light down to simulate what it would look like if we were traveling extremely fast over vast distances. As the speed of light slows, what becomes apparent to you? The first thing I notice is that the colors start to change. This is because of something called the relativistic Doppler effect. You see, when you look around and you see color on objects, this is because light is reaching your eyes at specific wavelengths. The longest wavelengths you can see are reds. The shortest wavelengths are violets. Beyond the range of our sight are the infrared and ultraviolet. But when you are going very fast, because of the Doppler effect, some of the wavelengths that were in the infrared and ultraviolet now shift to wavelengths you can detect. Suddenly, things that were invisible to us before become visible, like heat in infrared and fluorescent substances in ultraviolet. The faster you travel, the larger your visible range now becomes. Light does travel in waves, but it is also a stream of particles called photons. As you head into the flow of particles at speed, the more particles will hit your eye, making everything ahead of you brighter. On the other hand, if you look behind you as you travel forwards, everything will get darker because less photons are reaching you. This is known as the searchlight effect. What else do you start to notice? You may notice that we seem to be gradually speeding up. But actually, our speed always stays the same throughout the game. We are just walking like we were at the beginning. This is the result of special relativity, namely time dilation. One of the laws of the universe is that the speed of light is a constant. However, space and time are not, and can be warped. So when you are moving, two things change: your time and your distances relative to stationary observers. Let me explain. Time goes slower for an object that goes faster. This has been proven. If you have two clocks, one stationary and the other in rapid motion, say on a rocket, the times on each will go out of sync. This is why the times on satellites in orbit around Earth need to be occasionally adjusted, or they'd go out of sync with Earth-based clocks. Not by much, a few milliseconds per year, but they would add up eventually. The faster you go, the more time dilation happens, until, should you hit the speed of light, the rate of time reaches 0. This means photons, or light particles traveling the speed of light, are unaffected by the passage of time. But let's go back to how time dilation affects us in the game. Removing the lighting effects will help us see this a lot more clearly. Now remember, throughout the game, our walking speed stays the same. It's the speed of light that slows down as we collect more orbs. And yet, it seems that we move a lot faster towards the end of the game than at the beginning. What is happening here is that our time is going slower than everything around us. As a result, it's like the distances of space are shorter, meaning we get somewhere quicker from our perspective. In practice, this means that if we traveled in a vehicle that approaches the speed of light, we travel for 1 year at that speed, it all seems normal for us, but 10 years have passed for people on Earth. Should you actually be able to travel the speed of light, you could get anywhere in the universe instantaneously from your perspective, but on Earth, however far in light years your journey takes you will equal the equivalent amount of years from their perspective. So, do you want to go 40 light years away and can travel the speed of light? You get there instantaneously from your perspective, but for people on Earth, you show up there 40 years later. Again though, in practice, light speed travel is impossible for anything made of matter. The last effect is a weird one. It's like our field of view changes. This is from the effects of the aberration of light and the Lorentz transformation. Light takes time to reach our eyes, and when we see anything, we are seeing that object in the past. Even now, you are watching this video with a tiny time delay, as light takes time to leave your screen and reach your eyes. As we move in the game, that object we are seeing isn't where we think it is anymore. You may have thought as you've been watching this video that I must be useless at computer games because I keep crashing into walls and missing orbs. But this effect means that I'm not standing where I think I am, because the more orbs I have, the slower light is traveling. So I actually need to start turning a little ahead of what I'm used to, which is difficult to comprehend while navigating. It's like playing with lag. This effect also means that I can see much more of my surroundings in one go. This animation helps show why. The light source is moving relative to me as I move forward. But because the beam of light takes time to reach me, I see where it was relative to me in the past. When there is a lot to see around me, it's as if my field of view increases the faster I travel, as I'm suddenly seeing all these objects as they were relative to me in the past. Light, space, and time get more complicated still, but I won't delve into it in this episode. All I can say is that I'm glad light appears almost instantaneous for us. This game was a bit of a thought experiment to see what the world would be like if light was slow, but it hasn't even gone into the other really problematic scenarios, like Earth traveling around the sun at the speed it does, how all our electronics would be affected, and other major issues. In the opposite vein, us being able to approach the speed of light would be beneficial for traveling large distances in short times. However, time is passing normally for people on Earth, meaning traveling anywhere in the universe and coming back again could be possible for you, but Earth would look a lot different on your return, with years, decades, millennia, or more having passed depending on how far you went. On your journey, due to the various effects, outside your ship everything would look warped, your field of view would be greater, a greater range of light wavelengths become visible, and in front of you would be much brighter. So there we have it, how your universe would change if you approach the speed of light. Time moves slower on Mercury than it does on Earth. A day on Mercury is 58 days, 15 hours and 30 minutes on Earth. We can tell this by observing Mercury through telescopes and timing how long it would take for Mercury to complete one full orbit around the Sun. However, if we traveled to Mercury and started our timer there, we would not get the same figure. This is because time does not move as constantly as you might think. It can be affected by speed. The faster you go, the slower time goes for you. But it can also be affected by gravity. And Mercury is much closer to a massive source of gravity in our solar system, the Sun. But how much does gravity affect time? Could we live to incredible ages if we all went to live on Mercury? I'm McColgan and you're watching Astrum. Join with me today as we answer this question and explore the strange and warping world of general relativity and gravitational time dilation. I hope by the end of this video to have earned your like and subscription. To begin with, what exactly is time? Mark Twain once said that time is what keeps everything from happening all at once. It separates yesterday's events from today's, and today's from tomorrow's. As you sit here and watch this video, you are not doing what you were doing yesterday or tomorrow. You are watching this video. You are constantly traveling through time in the direction of the future at the rate of 1 second per second. This is the normal speed for traveling through time and is shared by you and everyone else on the planet. But this speed doesn't have to be the case. As discovered by Albert Einstein, the faster we travel through space, the slower our time becomes, up until the point where if we somehow could travel at the speed of light, time would stop moving for us. If we were to travel to an object 4 light years away from us, to people here on Earth it would look like it took us 4 years. To us, it would look like we arrived at our destination instantaneously. Although this sounds incredible, scientists have proven that this actually happens. They took 2 clocks. One they put on a plane and flew around the world with it on board, increasing its speed for an extended amount of time, while leaving the other at a stationary location. When they eventually returned and compared the clocks again, they found that the clock that had traveled faster had actually recorded less time, in line with what general relativity had predicted. General relativity is a real thing. But Einstein also predicted that this would happen with gravity. The closer you are to a large source of gravity, and the more mass that source of gravity has, the slower time will go for you. This was proven to be correct in 1959 with the Pound-Rebka experiment, where they shot gamma rays from the top of a tall building to the bottom and recorded whether anything had happened to the light waves. They found that the frequency of the waves increased the closer to the Earth they were. Kind of like cars bunching up in congested traffic, the peaks of radiation moved closer together. Time slowed down ever so slightly for the gamma radiation the closer it got to the Earth. This effect is significant enough that satellites have to be programmed to account for it, because when they are further away from the Earth's gravity, time moves more quickly for them. Without this correction, their internal clocks would go out of sync with our clocks on Earth, which would cause problems. And yes, that's right, the Earth's gravity is enough to cause time to slow down for us. So you're probably now thinking, how much faster would time be going for me if I wasn't on Earth or if Earth had no gravity? Well, it's a matter of perspective. The precession of time will always appear the same from your perspective. You won't feel like you're going slower, although you may notice some weird stuff going on around you. But it's the outside observer that has to deal with you slowing down. To find out an exact answer to the question, Einstein devised the following equation. We will be using this equation a lot in the rest of the video, so let's try to understand it. It looks a little scary, but it's not as bad as it looks. T0 is the answer we're looking for, how much time would pass on the object we're interested in this case the Earth. Tf is how much time would pass in a place completely unaffected by gravity. Such a place doesn't exist, by the way, but it is our hypothetical stationary clock. G is the gravitational constant, a number they added to basically make the sums work out. We're not going to worry about where it came from, all we're interested in is the fact it's always this. And don't worry too much about that metric at the end. M is mass, specifically the mass of the object creating the gravity. R is the distance from the center of the object, and C is the speed of light, a figure we know to be roughly 300 million meters per second. So to find out how much slower time goes on Earth compared to somewhere where there was no gravity, all we have to know is how much mass the Earth has, how far we are from its center, and then we can decide how much time we want to compare. Just to ease ourselves in, I decided to try this formula out with 60 seconds. If 60 seconds passes in our place unaffected by gravity, how much time passes on Earth? I plugged in the information and got our result. For every 60 seconds that passes, people on Earth experience only 59.9999996 seconds. In other words, 6 billion seconds have to go by before we notice a difference of 4 seconds. This happens roughly once every 190 years. So realistically, you'll only gain about 2 seconds over the course of your entire lifetime because of the Earth's gravity compared to a place with no gravity. This is a little underwhelming. However, we here on Earth are not just affected by our planet's gravity, we are also affected by the gravity of the Sun, which in terms of our equation is much more significant. So let's try this again by inputting the mass of the Sun and our distance from it into the equation. This gives us the new figure. How much time goes by for us on Earth for every 60 seconds of actual time that goes by? 59.9999994 seconds. While this is a more significant number, it does mean that you are only seeing a difference of a second once every 3 years or so. Or in other words, about 24 seconds over the course of an average human lifetime. But Mercury is much closer to the Sun. Surely time is significantly altered here compared to Earth with a massive object like the Sun so close by. How much more does time slow down for us on Mercury? The equation is essentially the same as before. The only new number we need is the distance between the Sun and Mercury. The answer to our final question of how much time passes on Mercury every 60 seconds is 59.99999 seconds. 60 million seconds need to go by before there's a single second's difference. This happens roughly once every 1.9 years, which scaled up across a lifetime equates to about 38 seconds difference. Only 14 more seconds than Earth. But from your point of view, you're not really gaining those seconds, because from your perspective, time would be moving normally. It would be the Earth that is moving ever so slightly faster from your point of view. So if you pointed a telescope towards Earth, you'd see 14 more seconds of Earth in history than you would if you were living there. As Mercury is fairly inhospitable, this probably isn't worth it. So, does Mercury's proximity to the Sun allow time to move slower for you compared to Earth? Yes, but only by a difference of about 14 seconds over your entire lifetime. In reality, time dilation due to gravity is not actually that significant, at least not in our own solar system. The mass of the Sun is not enough to really stretch time that much for us, even if we were as close to it as Mercury. The Sun would need to be millions of times more massive before we would begin to experience time dilation to any significant degree. However, it's still a fascinating insight into the way that time flows in our universe, and reveals that time is not as constant as we might think. And of course, it begs one final question. Are there any objects in the universe that are massive enough that we'd experience significant time dilation around them? There are. And this is where things start to get very noticeable to an outside observer. At the center of galaxies exist objects known as supermassive black holes. These objects have masses that are millions to billions of times the mass of our Sun. In other words, if you were to fall towards them, time could slow down for you so much that it would approach zero. If you were to get close enough to one of these giants and later escape it, you could spend half an hour around there and emerge to find that hundreds of years had passed to the people back on Earth. People on Earth with a powerful enough telescope would see you barely move. Even your breaths would take days to complete. In fact, there would be a point right at the edge of such a body that as you approached it, your time would hit zero. What would happen if you passed that point? Our equations break down and so cannot explain what lies beyond that horizon. Science does not yet have the answer, although there are certainly many theories. But that might be better explored in another video. General and special relativity can be pretty confusing topics, but was this video good at helping you digest this topic? And is this something you'd like to know more about? Let me know in the comments below, and if you found value in the video, please consider giving it a like and subscribe. What is time? In this channel, we've talked a lot about time. As black holes warp space around them, we've learned that time slows down. We've discovered the time-influencing effects of gravity and even how the James Webb Telescope can peer through time to the distant past by taking advantage of the fixed speed of light. All this makes sense so far, but what actually is time? You can't taste it, touch it, or feel it, yet time has an unstoppable influence on us and is pushing us forward whether we like it or not. Doesn't something that impacts everything we do deserve some additional understanding? I'm Alex McColgan and you're watching Astrum, and while this is an area that scientists have many theories about, I'd like to share with you today one model that might help you understand this mysterious concept that is ticking all around us. By the end of this video, we are going to have a possible explanation for why time slows down as velocity increases, and why shapes warp when undergoing velocities close to the speed of light. This video is a collaboration with my brother, based on recognized scientific theory, where we have taken scientific concepts and combined them into something you may not have seen before. But before we get to that, we have to begin with one foundational idea. Time is actually another dimension. Now, before you double check that you haven't logged into some sci-fi channel by mistake, let's discuss what I mean by dimensions. While in popular culture, different dimensions are often described as parallel worlds that are very similar to ours, yet subtly different. In this context, when we talk of different dimensions, we are referring to the dimensions of space, as in three-dimensional space, or 3D space, which may be far more familiar to you. This is by no means trivial though. 3D space is all around you. It is the around you, and is very relevant to our topic. Let's begin by making sure we understand the 3Ds and the relationships between them before we add the fourth D. Broadly speaking, 3D or three-dimensional space simply refers to space that can be measured in three different perpendicular directions. The perpendicular nature of these dimensions is important, but we'll get to that later. Three-dimensional space is usually described as having height, width, and depth, and they all have 90-degree angles between them. Simply put, objects like us that exist in 3D space can move left and right, up and down, and forwards and backwards. We are comfortable with this kind of space. Using this as our basis, it becomes much easier to imagine what we mean by 2D space and even 1D space. To move from one space to another, all we need to do is remove or add an extra dimension of measurement or movement that must be a 90-degree angle from all previously existing angles. So, 2D objects move in a plane that's bounded by the X and Y directions, or the X and Z directions, or the Y and Z directions, but not all three at once. 1D objects can only move either along X or Y or Z. Imagine a person who lived in such a 1D world. Their whole existence would be found either moving one way or the other. All of reality would exist either to the left or to the right of them, and would appear as a singular dot. They could not move or see in any of the other directions, and probably could not even comprehend such directions as even existing. Photons whizzing by them would only be visible if they entered the singular line that was a 1D person's whole area of existence. Now, adding extra directions of movement is what's needed to move things up from 1D to 2D to 3D. So, in theory, we can predict what we need to do if we were to jump to 4D. However, here we hit a snag. While it's easy to draw a line that's perfectly perpendicular to a single other line, or to draw another line on top of those lines that is perpendicular to the two previous lines, how would we draw a fourth line that's perpendicular to all three? Surely such a thing is impossible. Well, within 3D space, such a thing is impossible. The best we can do is draw approximations. For instance, it's possible to draw an approximation of a 3D shape on 2D paper by doing something like this. These lines are all two-dimensional, but we look at this and our brain recognizes that this is a picture of a 3D shape.
So in the same way, we could probably do something similar to what a 4D object might look like using just 3D lines. Mathematicians have attempted to do this, although their results tend to be a little confusing. Although this is mathematically sound as a basis for a 4D object, I personally don't find my understanding of 4D space deepened by looking at it, so I won't focus on it in this video. There is some evidence, however, that a fourth direction exists, and we are moving along it right now. That fourth direction, or dimension, is time. Einstein predicted this connection when he linked space and time into one unified space-time in his theories of relativity. According to him, time and space are two parts of the same thing. To me, this connects with 4D space very nicely. Just as there is no real difference between the Z and the X or Y directions, so too would there not be any difference between time and space if time is just another direction, albeit one that we can't see. And time is important. Without time, our 3D space wouldn't move. It would perpetually be in one state, because it's time that allows us to move about in it. But why can't we see it? Why can't we look in the direction of time? To explain this, let's look at the difference between the different dimensional spaces. We best notice this when we consider what 2D objects might look like if they were to move around in 3D space. This is where we start to delve into the model. Let's begin by visualizing a standard 3D space. But because we want to eventually see all of space and time in one model, let's cheat a little. Let's compress all of 3D reality as we know it into a flat, two-dimensional place. In this plane, let's make that our XY plane, which we will label space, which frees up the Z dimension for time. In this model, all 3D people are now just 2D. A 2D person could exist and live their lives in the place marked space at the bottom of our chart. However, by moving them up on the chart at a constant rate, they are also moving through time. Let's for ease and convenience say that the top of our diagram is the future, while the bottom is the past. So the higher up our 2D person goes in this diagram, the older they get. As we don't seem to have a whole lot of control over our ability to travel through time, let's imagine for a second that our 2D person travels upwards at a constant rate, as if there is some consistent force or wind at play pushing them upwards towards the future. Sadly, we cannot slow down time for ourselves simply through willpower, no matter how much we might want to do so. However, it is misleading to say that we can't change it at all. The faster we travel in space, the slower we travel in time. This is one of the guiding principles of Einstein's relativity. This model can express this idea through the power of vectors. As our 2D person tries to move to their left or to their right, their vector of travel changes. While traveling at a fixed rate, like a sail on a ship catching a breeze, we can only go as fast as the wind takes us, so the vector coming out from their front must always remain the same. To travel the fastest through time, our 2D person must orient his vector completely in the future direction or upwards. However, if they are to travel any amount in either direction to their sides, they can only do so by pointing their vector away from their direction of travel. They have motion in the X direction now, but they have done so by reducing their motion in the Z direction. They are moving through space, but at the cost of moving a little slower through time. Taking this to its furthest extreme, our individual has completely flipped on their side and now only has motion in the direction of X and none in the direction of Z. They have velocity in space, but not time. So I suppose this implies our vector is the speed of causality, or the speed of light. If this is the speed we're talking about, then moving at low speeds through space would not have any noticeable difference in our speed through time. We'd have to go really fast before we started to notice anything. The vector still mostly points upwards. An interesting result of this model is that, from the 2D man's perspective, nothing has really changed. He has his own view of what reality is. For him, the vector coming out of his chest is still time. The dimensions of the plane he's lying flat on is his space. To him, it's the rest of the universe that's gone a little weird, but he himself is perfectly normal. However, once he reorients himself, it is clear that the rest of the universe has moved on without him. This is clearer if we add a second 2D person. Initially, both of our individuals do not move in space. All of their vector is pointing in the direction of time. Nothing that strange seems to happen so far. However, if our stick man on the right turns and vectors at near the speed of light for a bit, then reorients himself, while the second 2D man on the left just stays where he is, it becomes clear that our 2D men have not moved at the same rate through time. Assuming that our two stick men can somehow still see each other, let's imagine that they somehow project an image of themselves onto the other person's space plane. They immediately notice that there is a difference in age. The one who traveled at the speed of light did not advance so quickly through time as the other, who remained stationary and so is younger. But why do we find this model so compelling? Well, it is because of what those projections would look like during changes in direction. From the point of view of the first stick man, initially the projection of their friend seems fairly normal. However, as they start traveling very quickly in space, and their vector oriented in a direction away from time, a 2D shape reveals its inherent flatness. And from a face-on perspective, it goes from this to this. The speedily traveling stickman appears to flatten, with an effect that's more pronounced the faster they go, and the flattening takes place in the direction of their travel. The stickman who remains stationary might wonder at the strange change that is occurring to their friend, never comprehending that it represents a reorientation of a 2D figure in 3D space. Now, what captures my imagination about this is that this same thing happens in real life. According to Einstein's theories of relativity, objects traveling at great speeds in 3D space would appear from an external observer to flatten in the direction of their travel. This squishing effect happens exactly in line with this model, and is to do with time dilation. However, from the person who's traveling's perspective, they do not flatten, but it is the rest of the universe that warps. I talk about this in greater depth in another video of mine, where we can see the effects of spatial warping in a computer model. From their perspective, everything would stretch at the edges of their vision, while their destination would seem further away, which is again what this model would predict. The only difference is that in this model, we're just exploring a 2D object stretching. So the stretch is only in one direction, while in real life it's 3D, which means it stretches in two directions instead. But that is what you might expect as you turn away from our conventional 3 dimensions and start orienting yourself away from time. But if this is correct, so what? Why does it matter? If time is truly a direction, then it deepens our understanding of the universe. It also raises more questions. What is the force that pushes us ever forward in time? Why does it seem that we can never move against it? Although in this model there is no reason why a vector could not point downwards, in real life that doesn't seem to ever happen. This model also answers the question of, if time is a direction, what is our shape in time? Does part of us protrude into the past or into the future? According to this model, that does not happen. We are flat pancakes in the 4th dimension, pennies that look round when you look at us head on, but revealing our thinness when we turn away from you. That's a strange thought, but it may just be true. This might explain why we are unable to see through time. We just don't extend enough in that direction for it to be visible. Your form might be quite different than you first thought. Of course, this model is just a theory of ours, although we have tried to base it on scientific observations and conventional theory. But what do you think? Does this model help you make sense of time as a 4th dimension? Please leave your ideas in the comments below on the nature of time and what it might actually be instead. I hope to explore more strange concepts like this in a new series called The Unseen World, where I want to explore the shape of reality around us. While it's normally invisible to us, the shape and dimensions of the universe can explain why things are the way they are, and I'm excited to explore it with you. If you are interested in it, let me know. If there's one thing I've learned about light, it's that for unthinking energy, light seems to love messing with us. For years, scientists debated about whether it was a particle or a wave, because it keeps exhibiting elements of both, seemingly unable to settle. It behaves one way when you're looking at it, but a different way when you're not. But at least its speed is consistent. Light travels at the speed of light. No matter your frame of reference, that one thing remains the same. Except, no, it turns out the constancy of light speed might not be right either. Light might go slower than physics would predict in certain circumstances. And no, I'm not just talking about light slowing down in denser mediums like glass, although that's what I originally intended this video to be about. We have an explanation for that. I'm saying that in some circumstances, light seems to travel a path through time and space that has it either going slower or faster than the speed of light, even if dense mediums aren't present. But the really weird thing is that it ends up at the same destination in space and time anyway. I'm Alex McColgan and you're watching Astrum. Allow me to show you what I mean. Thanks to a new take on the double slit experiment, I want to show you that your understanding of light is either incomplete or, well, wrong. Light travels at 299,792,458 meters per second. According to relativity, this is the only speed light can travel at, and interestingly, seems to stick to that number regardless of your frame of reference. Two people could be traveling through space, one at 1% the speed of light and the other at 50% the speed of light. But if they both look at the same beam of propagating photons, they will see them traveling at the same speed. Time and distance would seemingly rather warp than allow you to see anything other than light traveling at light speed. Of course, when scientists say this, they are only talking about light traveling in a vacuum. We've known for a long time that as soon as you get matter involved, light gets bogged down and travels slower. Light traveling in air only goes at 299,705,000 meters per second, a full 87,458 meters per second slower than light in a vacuum. Light in water goes around 225 million meters per second. Light going through glass caps out at around 200 million. The reasons for this are intriguing, but fairly well understood, and certainly not physics breaking. When light travels through matter, its constantly waving electromagnetic fields gets the electrons within the matter to start moving, like ships bobbing on water. But as electrons moving up and down also generate an electric field that in turn creates a magnetic field, a second light wave is created by these moving particles that crucially overlaps the waves of the original light, albeit one that waves at a slightly different pace to the original light. Exactly what speed varies depending on the material. When two waves meet, they interfere with each other. They take an average, sometimes interfering constructively to build each other up, and sometimes working against each other. So when you take the grand total of all the ups and downs of each wave, you actually end up with a new wave, one that travels at a different speed to the other two, and one that goes slower than the speed of light. Eventually, this propagating wave can reach the edge of the blocking material, and without those electrons interfering anymore, you're left with just the original light again, which is then free to travel along its original path again, at its original speed, as if nothing had ever happened. Scientists have had a lot of fun with this concept over the years. Researcher Lene Howe at Harvard in 1999 was able to slow down light to an astonishing 61 kilometers per hour by sending it through a cloud of sodium atoms that had been cooled to 1 billionth of a degree above absolute zero. 2 years later, Howe managed to slow down light speed to 0 before warming up the cloud and sending it on its way again. You might find that result surprising. However, strange things have happened in the opposite direction too. In 2000, researchers at the NEC Research Institute in Princeton, New Jersey, sent a pulse of light through a cloud of cesium atoms. Alarmingly, when they tried to see how quickly the pulse exited the cloud, it seemed that it exited before it had entered. While this might appear to mess with causality, how can you leave a building before you go inside it after all? Fortunately, there was a simple explanation that saved us from creating too many paradoxes. Although the light pulse traveled faster than light, the light itself did not. This was more an optical illusion than a refutation of Einstein's relativity. Let's take a closer look at a photon of light. Each photon represents a tiny packet of waves, moving up and down. The speed the waves inside the packet propagate is known as its phase velocity, while the speed at which the packet as a whole is traveling is known as the group velocity. You can also have a wavefront velocity, which is how fast the first photon in a wave of photons can travel. This is a little heavy in its terminology, so let's explain it with an example. Think of a crowd of people doing a Mexican wave. The wave that the people are doing is the phase velocity. You can see the wave traveling along through the crowd. It might look like it's traveling quickly, but the crowd itself isn't going anywhere, so our wave's true speed is 0. These people are the group velocity, or possibly the wavefront velocity. Let's imagine that we wanted to send our crowd marching. They could do so and could keep doing a Mexican wave as they traveled. But although their waving hands might make the wave go really fast in the direction of their travel, it would vanish whenever it reached the front of the crowd. Information exchange couldn't go faster than the walking speed of the crowd itself, regardless of how fast the peaks in the wave seemed to be traveling. Einstein in relativity never claimed that phase velocity couldn't exceed light speed. He just claimed that information couldn't travel faster than light. And if you're trying to deliver a message to someone by sending a crowd of Mexican wavers in their direction, it really doesn't matter how fast they're waving. Until the first person in the crowd arrives, no information can be delivered. Still, this difference between the waves within light and the speed of light itself will become interesting in our next experiment. And this is where things start to get a little weird. Oh, you thought it was weird already? Oh no, this is the really physics-defying part. Let's go back to an experiment we've looked at before, the double slit experiment. I go into more depth on this experiment in my video here. If you haven't watched it already, I really recommend you do so, as I'm going to assume you know what this experiment is for the part that comes next. This experiment is a fascinating exploration of how light can sometimes behave like a wave and sometimes like a particle. However, in 2023, researchers from the Imperial College figured out a way to separate the slits of this experiment, not in space, but in time. The way they did this was simple. They took a transparent material called indium tin oxide that, under specific conditions, can be made to be reflective. Indium tin oxide is the stuff they use in most mobile phone screens. They fired a laser at it, and then rapidly changed the material from transparent to reflective and then back again. This left only a slim window, a few femtoseconds, where the laser was reflected. They called this a time slit. They recorded what the laser looked like after it had been reflected, and found that its frequency had spread out a little bit in the process, but other than that, nothing too crazy had happened. The weird thing was what happened when they sent 2 laser pulses through these time slits in rapid succession. The position of the emitter, the mirror, and the receiver remained the same. The only thing different was the time the lasers went through. Oddly enough, when 2 went through, an interference pattern happened. This was not an interference pattern in the same sense as with the regular 3D space double slit experiment though. This was an interference pattern that had affected the laser's frequency. Certain frequencies of light within the laser faded out, exactly in line with the way intensity faded out in the regular version of the double slit experiment. To visualize why this might be happening, let's draw out this experiment in regards to time. The time slit experiment can be drawn in a similar way to the double slit experiment, except we are going to need to visualize the change in the experiment over time. To do that, let's create a 4D graph where space is along the x-axis and time is along the y-axis. This is easy enough to do. It just looks like this. The photon leaves the emitter to the left, hits the time slit, is reflected, and arrives at the receiver. I've drawn this as a continuous line just to make things simpler later, but the idea works just as well either way. Later, a second photon is released from the emitter. It reflects and arrives at the receiver at a slightly later time, represented in how it takes place higher up, further into the future on our time graph. If light behaved normally, traveling along at the speed it was supposed to go at, this would be the end of it. Instead, light is interfering with itself. This means it must be traveling along a path that takes it through the other slit as well as its own. This is the only way that light could come in with the pattern that we see. And just like in the double slit experiment, it's likely happening on the other side of the slits too. As for why it's frequency and not intensity that's being messed with here, think about the implications of what you might see if light did indeed come in at a different angle like this. Photons come in little packets of waves, as I've previously mentioned. Now look at what happens if you change the angle at which those waves arrive. Here's how it normally might look. I've added a black timeline here and have highlighted every time the receiver receives a new peak in the wave. Here's what happens when you alter the direction of the wave's arrival. Suddenly, the peaks are coming in much more frequently. The frequency of a wave over time is very much connected to the color we perceive light to be. Lower frequency light is redder in color. Increasing the frequency shifts light's color towards blue. So this color variation makes sense. What makes less sense is what's going on with the paths this light is taking through time. Remember, the straight lines we started with represent the 299,792,458 meters per second that we see light traveling. So what can we say about the photons that are traveling along these paths? For some parts of their journey, they are traveling slower than the speed of light, taking more time to arrive at a destination that's the same distance away, and yet, for other parts of their journey, they are traveling faster than causality ought to allow. From their perspective, they are traveling backwards in time. As a reminder, these two emitters on the left are actually the same one, just at different points in time. The same for the receivers on the right. It is a mind-bending result. And yet, according to the results of this experiment performed by a research team at the Imperial College in London, this is what is occurring. The implications of this are startling. Light always travels the path of least time, the route that allows it to arrive at its destination along the path closest to 299,792,458 meters per second, the fastest anything in the universe apparently can go. And yet, it seems that in its efforts to locate exactly what path that might involve, light is testing the waters, putting out feelers that check to see if other paths, and seemingly other paths through time itself, might present a more viable solution. These feelers are interfering with photons that travel alongside it, but also with photons that travel a little ahead or behind it in time. To be clear, we never actually detect photons taking any of these other paths. We don't see photons coming in from the future. We never see photons traveling slower than the speed of light, provided there is no supercooling gases providing an explanation for why they slow down. And yet, for interference patterns to occur, to at least some extent, light must be trying out alternative routes through time. Perhaps it's like lightning, testing many different directions to find the optimal path for its destination before finding the one that works and collapsing down that path in one giant boom, all other feelers vanishing and collapsing. Or perhaps some other phenomenon is at play. Who can say? For now, all we know is that light has proved once again that it doesn't play by anyone's rules, at least not rules that we can figure out.
Can information travel backwards in time? It's the sort of thing that would be really useful if it were true. You could tell your past self not to eat that burrito that didn't agree with you, or you could reveal to yourself the winning lottery numbers. But it just doesn't happen. The resulting paradoxes alone would make the whole thing laughable. In our universe, time always seems to flow in one direction, forward. The idea of traveling backwards in time, or even simply communicating with your past self, seems so outlandish, it can't possibly be true. So, why is it that on the quantum level, information seems to be doing just this? What? You haven't noticed particles communicating backwards in time? Well, perhaps we need to talk about the strangeness that is quantum mechanics. It is an effect that, if understood, could one day bring us technologies like faster-than-light communication, or faster-than-light travel. At least, if we could somehow harness it. But even if we can't, it's an undeniably strange insight into the unseen world around us. I'm Alex McColgan, and you're watching Astrum. You're about to see some real-world experiments that are mind-bendingly weird. And if by the end of this video you enjoyed what you learned, feel free to give this video a like and subscribe to the channel. Just please don't break causality when you do. So what do I mean by particles traveling backwards in time? By all accounts, it doesn't seem possible. In previous videos, I mentioned that objects would require infinite energy to even go fast enough to reach the speed of light. So how could something go so fast as to reverse the usual direction of time and arrive at a destination just not instantly, but before they left? Not even light can do that, and it's the fastest thing we know of. Well, this rule about nothing traveling faster than light is mostly true for the macro-scale universe that we live in, and by macro-scale I mean everything significantly larger than an atom. But physicist John Stuart Bell noticed an exception to this rule when it comes to quantum entangled particles. Okay, so let's start there. What is a quantum tangled particle? In quantum physics, it's possible to hit two particles together in such a way as to link them together, so that by measuring the one particle, you learn things about the other. For instance, if you know that the particles originally had a total of 0 momentum, and you learn the momentum of one of the newly quantumly tangled particles, you know the momentum of the other particle will be the exact reverse, making sure the total remains 0. Effectively, by measuring the one particle, you can learn things about the other. This works for other particle properties too, such as position, polarization, or spin. On the surface, there's nothing too weird about this. It's no different from me meeting up with a friend and discussing our plans for the evening. We agree to go out, and we agree that I will pay for the evening and my friend won't. Then, no matter how far we go on our night out, or even if at some point separate, I know I will be paying and my friend will know that he won't. This is how Einstein thought it worked, only it turned out that Einstein was wrong. Because as it happens, me and my friend did not discuss in advance who would be paying. And the strangest of all, we still both agree with each other anyway, 100% of the time, no matter how far apart we are. This is the strange thing about quantum entanglement, and quantum physics in general. We like to think of particles as having fixed properties. However, our first mind-bending experiment shows that particles only have properties when you detect those properties. Until then, they're kind of vague about the whole properties thing, instead only relying on probabilities as defined by a quantum wave equation. This doesn't make sense intuitively. Looking at a thing shouldn't be what gives it properties, right? Well, how would you know? If a tree falls in the woods, does it make a sound? According to quantum physics, not necessarily. Let's talk about the first mind-bending experiment, the Bell experiment. The maths for this is pretty complicated, but bear with me, it's worth the ride. The experiment was first conceptualized by John Stuart Bell, who wanted to know if particles really did have secret properties that they carried around with them, known as hidden variables, or whether they really were making some of it up on the spot. He noticed an interesting mathematical fact about the spin of particles. Before we go any further, I should probably mention that quantum spin isn't the same as normal spin. Misleadingly, quantum spin actually defines whether a particle is influenced, pushed or pulled, by a magnetic field. The name isn't important, but it is important to note that these particles aren't actually spinning, and so can have different spin values in almost any given direction. Now, let's take two quantum entangled particles, and let's say that we've arranged it so that their spin adds up to a total of 0 between them. This means that if one particle would be pulled by a field, the other will be pushed by it an equal amount along that direction, with the understanding that this doesn't tell you anything about their spin in other directions. One of the features of quantum spin is that if we measure an entangled particle's spin in any given direction, let's say up and down, it will have a 50% chance to be spinning up and an equal 50% chance to be spinning down. But remember, once you measure the other entangled particle, it will have a 100% chance to be spinning in the opposite direction to the first particle. On this fact alone, there is no way to tell if the two particles already knew their spin or are somehow deciding it on the spot and conferring it with each other now that they've been asked. But Bell noticed a clever thing by asking a clever question. If you measured two quantum entangled particles from two randomly selected directions, what are the odds that their spin for different directions would match? Now, let's define that at any time a particle is spinning towards a detector, its spin is up, and any time it is spinning away from a detector, its spin is down. What are the odds that both particles would be spinning up or down when tested? And what are the odds that they would contrast? Let's formalize this with a little experiment. Here we have two entangled particles, with 3 detectors reading their spin in different directions. If particle A and B are both red with the top detector, then one of their spins will be up and the other will be down. They are entangled. This is what we looked at previously. However, if particle A is red using the top detector, while particle B is red with one of the other two, these two directions of spin aren't opposites. So particle B has flexibility in which way it goes. Quantum physics claims the particles are making up their attributes on the spot. So once you'd measured the spin of particle A using the top detector, it was a 50-50 whether the spin on the other particle using one of the other detectors would match or contrast. But this is not what classical physics predicted. Let me show you what I mean. Classical physics claims that particles each carry around secret information defining their spin in any given direction. So, for our 3 tested directions, each particle would have a value already. They aren't making it up on the spot. Let's say, hypothetically, our particle's hidden information states up, down for particle A and down, up for particle B, as B must be opposite to A for each of the directions 1, 2, and 3. Let's pick out a random detector for A. We select detector 1. Detector 1 tells us that A is spinning up. Now let's select a random detector for particle B. We select 1 there too. This detector gives us a reading of down. 1, 1, up, down. We can actually map out all the possible outcomes of this process of random selection in the graph. There are 9 possible outcomes if you were to only measure from 2 detectors at a given time. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and so on. For each of these possible selections, we have fixed hidden variable results that we know already, because we hypothetically defined them earlier. Let's fill them in now.
Of course, if you detect particles using the same detector on both particles, you'll get a contrasting result because they're entangled. But we're not interested in these results. Classical physics and quantum physics both agree on this, so let's remove them. What are the odds that two different detectors for particle A and B will see the same result, and what are the odds they'll differ? Remember, quantum physics expected it to be 50-50. Particles are making up their values on the spot, and so it's perfectly random which they'll choose, as they aren't confined by the opposites rule here. But in this table, classical physics says that contrasting results only happen a third of the time. The other times, they're either both up or both down. If we do this many times, assigning different directions each time, and ignore exceptions, for instance, where the spins of the particles are all up, 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 or down, 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 once you crunch the numbers, the important thing to take from all of this is that according to the maths, classical physics predicts a matching outcome 55% of the time, while quantum physics continues to simply predict 50%. Pretty table be damned. This percentage difference was the key. By quantumly entangling particles and running this test over and over again, you could now see which percentage was correct. And it turned out the winner was quantum physics. Particles were just apparently making up their spin results on the spot, which is spooky. Because not only does that call into question our perceptions of reality itself, but that also means that the moment one particle decided on its spin result, its quantum entangled partner instantly knew that that decision had happened. You could test both particles at once, no matter the distance, and this same result would come back. Somehow, information had traveled from the one particle to the other in no time at all, far faster than light itself. So already something strange was going on here. This result disproved Einstein's predictions and showed that some information does seem to go faster than light. But we can take this one step further and have information going back in time. There is another experiment known as the delayed choice test. Its primary purpose was to explore the fundamental nature of light, whether it was a wave or a particle, and to figure out when it decided to be one or the other. Experiments like the double slit experiment had done this in the past to mixed results. Sometimes light behaved in a wave-like manner, creating interference patterns on detectors that could only happen if a wave was interfering with itself. But sometimes it behaved like a particle, hitting only a single point on a detector. But most baffling of all, it seemed to change which it behaved like depending on whether you were observing its path through space or not. If it could go through multiple paths and no one was watching to see which it did go through, light simply went through both, like a wave. But observed, it went through just the one, like a particle. This result was baffling enough and deserves a video on its own, but in 2006 a number of scientists took it one step further by asking an interesting question. What would happen if you tried to observe the light after it had to pick a path? Consider this experiment. A single photon is sent into a beam splitter, with a 50-50 chance of either being allowed to carry on its way along path 1 or getting reflected up along path 2. Once on either path, the photon is bounced off mirrors, with both paths reconverging here, where the other beam splitter is inserted. Once again, the photon has a 50-50 chance to go either way, with an even chance of arriving at one of the two detectors. If light were just a particle, sending a single photon into this experiment would give you an even chance of it arriving at one detector or the other. You'd not be able to tell which way it went, as the two beam splitters make that impossible to know, but you could see where it ended up. However, this does not occur. When the second beam splitter is present, the light produces an interference pattern, indicating that the single photon went down both paths, ultimately bumping into itself before moving on to both detectors. This seems like strong evidence that light is a wave. It certainly behaves like one here. But what happens if you remove the second beam splitter? Suddenly, you know which path the light traveled down. If light arrives at the top detector, it must have arrived from path 1. If it arrives at the side detector, it must have come along path 2. And something about this knowledge spooks the light. It stops going down both paths, and suddenly, each photon only arrives at one detector. Here's the question. What happens if you insert the beam splitter after the photon has already started down either one or both routes? This is why the test is called delayed choice. If you delay choosing how exactly you intend to detect the photon, whether by knowing which path it came down, or making that ambiguous to you, what happens to the light? What happens is a very strange thing. When this experiment was performed, it was done multiple times, with the beam splitter randomly being inserted or not, but always being inserted after the photon had entered one or both paths. And yet, the results came back unequivocal. If the beam splitter was present, the photon suddenly and seemingly retroactively stopped picking a path. If the beam splitter was removed, the photon seemingly knew it would later be detected and picked a specific path to accommodate. Somehow, the beam splitter being added or removed in the future changed what the photon did in the past. So, what is happening here? Is it really true that particles somehow saw the future? Did the experiment cause information to be sent back into the past? Or is there some other principle at play here that explains this whole thing, that accounts for the instant transmission of information between quantum particles, and allows it to be perfectly rational that light could travel down one path or both at the same time? Personally, I'm inclined to think that this is more likely. We clearly don't understand what is happening here, but it must be admitted, if we don't understand what is happening, there's nothing to say that causality isn't being ignored. In some way, maybe on the quantum level, time really is more fluid than it is up here in the larger universe. Maybe space and time simply do not apply down there. And maybe one day, someone will be able to come up with a theory that allows all these strange phenomena to finally make some sense. Until then, we'll just have to keep asking the same question. Can information travel backwards in time? Until then, we'll just have to all agree on one thing. Quantum physics is strange. Thanks for watching. I was honestly blown away by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.